All right, so now that we have shown that P is a self-adjoint operator, we'll prove a very nice theorem. We'll actually prove two very nice theorems. One is that self-adjoint and Hermitian operators have real eigenvalues. Okay, so self-adjoint or Hermitian operators have real eigenvalues. Okay, so how do we do this? So let's take Hermitian operator H, and H is acting on some eigenvector and giving me an eigenvalue E. Okay, now suppose I take the, okay, before I do this, what I do is I then, so this is H of psi, I multiply it by the psi star or psi bra, and then E is just a number, so E doesn't partake in this inner product. So this equation leads to that equation. But I could have taken this equation and taken its Hermitian conjugate or adjoint. Then this equation would just give me this. Now, because H is Hermitian, what we can say is that we can write well, we can apply psi from the right. Then I will have H dagger of psi, and here I will have E star psi of psi. But H is Hermitian, and therefore I can write the left-hand side as this. Now what I do is that I take this equation and this equation, and I take there and subtract one from the other. If I do this, I get E. So the left-hand sides, these two guys cancel out, and then we have E minus E star psi by. Now we are assuming that psi is not the zero vector. If it's not the zero vector, then this is non-zero. If this is non-zero, then it must be that E is equals to E star. Okay, so this shows that every Hermitian operator or self-adjoint operator has eigenvalues which are real. Okay, so that means that, remember that we decided that one of the postulate was that, observables in quantum mechanics are represented sorry, what happened? Give me 1 second. All right. So observables are represented by Hermitian operators, and when we do an experiment, what we get is one of the eigenvalues of the Hermitian operator, and therefore all the eigenvalues are real numbers. Like, although quantum mechanics, complex numbers play a very, very important role in quantum mechanics. In fact, you can't really do quantum mechanics without complex numbers. It turns out that observables, as we, when we do experiments, we always get real numbers. Okay. All right, so this is theorem number one. The other theorem is about the orthogonality of states. And this is I'm going to prove a limited version of it, not the most general. And the idea is that if we have two states belonging to two different eigenvalues of the same operator, then they are orthogonal. So what do I mean? Say H is a Hermitian operator, and M is an eigenstate belonging to the eigenvalue En. And n is another eigenstate belonging to an eigenvalue En, now such that Em is not the same as En. Okay? So then what we can show is that the state N and M are orthogonal, meaning that their inner product is 0. So how do we do this? Well, from the second equation, we can take its Hermitian conjugate, and because H is Hermitian, we just get H here, and we get NE here and EN. EN is real, right? So then from the first equation, if I multiply it from the left by N, I get NH of M. And from the right-hand side, I get EM, N of M. And from this second equation, the last equation, I get NH, and I multiply it by M from the right. And then I get EN, N of M. Okay? And then what I do is that I subtract this two equation, and then this becomes 0. And from here, what I find is I get an M EM minus EN. Now, by assumption, EM and EN are different numbers, so this is not equals to 0. Therefore, this thing must be 0. Therefore, these two states are orthogonal. Okay? Very simple proof.